In this video, we're going to do a discussion about the heating curve that you guys did and the analysis of the phase changes, temperature areas, where's temperature. In this video, we're going to look at the heating curve that you generated and the analysis that you did on the data collected. So there's a lot going on here. I'm going to go through each area and give an explanation of what's going on. Make sure that your answers are similar to or parallel what I am going to be discussing, and we'll use this as preparation for your assessment that's going to be coming up next week. So we're going to start off at the beginning. This data here that I have from the 25 degrees Celsius in this area here, or negative 25, all the way up through this area here where we are melting the water. This was all done in the video that I posted dealing with those the melting of water and the discussion of that from negative 25 up through melting. So, but I'm going to focus on this area here. This is the first of 5 areas that we had on our graph that were very distinct. We can see that we start off at a temperature of negative 25 and we work our way up to a temperature of 0 degrees Celsius. This area that I have highlighted, this is where it is a solid only. There is no liquid here. For that to occur, you have to have water at least 0 degrees Celsius before you can have a liquid. Along with that, our kinetic energy, since the temperature is changing, is going to be increasing as the temperature is increasing as well. Remember, temperature is a measure of the average kinetic energy. So if our temperature is rising, our kinetic energy is increasing as well. That means that the molecules are moving faster. Now, they're still in a solid state, so they're still stuck in one location, but they're vibrating back and forth at a faster rate. Because they are moving faster, because they are vibrating more quickly, they are actually going to also be getting a little bit further apart, and their intermolecular forces throughout this entire area are going to be decreasing as well. So the strongest intermolecular forces are going to be down here where it's negative 25 degrees Celsius, and they're getting weaker and weaker and weaker, still strong enough to hold them as a solid until we reach this 0 degrees Celsius mark. In terms of the energy change, I'm going to zoom out because space. This was the calculation done to calculate how much energy it took to raise the temperature from negative 20, I guess I used negative 20 here. I think you guys, I can't remember, I think it was negative 20 degrees Celsius, all the way up to 0 degrees Celsius. So the amount of energy required to make that energy change was 8,400 joules. Now that is an input of energy because energy was going into that ice to get the temperature to rise. Our next area is going to include a couple of other extra things. Our next area of focus here is going to be this area here where the water was melting. So this area represents where we have both a liquid and a solid, because once we reach this temperature of 0 degrees Celsius, and you see I've labeled this area here as the melting point, okay? So once we reach this 0 degrees Celsius, then the water can begin to melt. And we're going to start seeing liquid water appear right around this point. And we're going to get more and more water as it melts. But the temperature is going to remain constant during that process. The other labels I have here, I can't remember how I have it labeled, but this is where it begins melting. This is where it has finished melting. This is where the first intermolecular forces are being broken. So remember, we have as a solid, the intermolecular force is strong enough to keep them as a solid, but here is where your first forces are being broken, enough to allow the molecules to start melting. As you can see, our temperature does not change. Because that temperature is not changing, that means that our kinetic energy is remaining constant. So again, temperature is a measure of the average kinetic energy. So if it's not changing, our kinetic energy is not changing. These molecules are not moving faster. Okay, again, they are not moving faster. What is changing is their actual motion. We're making that transition from a solid to a liquid. Liquid molecules can move past each other. They are not stuck in one place. They are still attracted to each other, but the attraction is not strong enough to lock them in place. So we've got our melting occurring. We've got the intermolecular forces actually being broken, so they're weakening and breaking up to allow those water molecules to move past each other. In terms of the energy calculation associated with this area, because there is not an energy or a temperature change, we're not using the Q equals mc delta T. You're given data about what the enthalpy of fusion is, and the enthalpy of fusion is used for calculating phase changes between the liquid and solid state. In this case, we have energy going into our ice to melt it. The 200 grams of water, this right here is your enthalpy of fusion for water. It was given to you in the lab, and it's 333.55 joules per gram of water. So for each gram of water to melt it, it would require the input of 333.55 joules. That corresponds then to 66,710, or 6.67 times 10 to the fourth joules. Our next area then is going to be where our water is a liquid only. So this area here where our temperature is going up. So once we have completed melting the water, so here we've got the last intermolecular forces broken. This is where it stopped melting. We've completely converted all of our ice into water at this point. So now that we have water at 0 degrees Celsius and it's just one state, we can increase the temperature. So in this, because you did that with a Bunsen burner, that time frame that it occurred in is very quick. Obviously, the highest the temperature that would have gotten without a Bunsen burner would have been room temperature about here, but that would take quite a bit of time. But having a Bunsen burner increases that rate, so our time increments are very narrow here, but our temperature change is changing very quickly. So again, liquid only in this area here. This is where our last forces were broken. This is going to be where our boiling begins, and we'll get to that in a second. Because our temperature is changing in this area, our kinetic energy is increasing. That means the molecules in this area here, they are increasing in their velocity. Their motion is still contained to the liquid. It's still a liquid, but they are moving more quickly. And the intermolecular forces, again, are continually, throughout this entire process, they're continually getting weaker. Because the temperature is increasing and the molecules are moving faster, they are also getting further apart. So throughout this entire process here, the intermolecular forces are getting weaker. Weaker until we reach our 100-degree mark. Now for our energy value, we're going to have Q equals mc delta T because our temperature is changing. So we can use this equation. We've got our mass of water 200, specific heat given to you in the lab as 4.184 for liquid water, and we have a temperature change of a final temperature of 100 and our initial temperature at 0, because again, if we go back and look at this, we're at 0 degrees Celsius and we're going up to 100 degrees Celsius as a liquid. That gives us an energy of 83,680, or 8.37 times 10 to the fourth joules. Okay, our next section here is probably going to be very short on this graph because of just the time scales. That's why I had you guys make some adjustments with adding some data there. So you're probably going to have a large gap in here, may even be larger than what mine is. But at the beginning here, throughout this entire process, we've got a liquid and a gas. So this right here represents the boiling of the water. We can see this is where we have the boiling begin. This is where we're going to have the boiling end, or some data point near that, because boiling is going to occur at 100 degrees Celsius. You can see I've got that labeled up here. So this is also where our first intermolecular forces are being broken for the boiling process. And one of the significant differences here compared to where ice was melting is that we are literally breaking every attraction now. We are causing this liquid to separate into a gas. And in a gas, as we will learn in our next unit, we really do not have any intermolecular forces to speak of between gas molecules. So that means in this process, we are breaking those intermolecular forces completely. That will, as we will see here in a minute, mean that our energy change is going to be significantly greater to do the boiling than it was for all the other parts that we've seen so far. In terms of the kinetic energy, because the temperature is not changing, our kinetic energy is not changing. Remember, again, temperature is a measure of the average kinetic energy. No temperature change, no kinetic energy change. That means the speed of the molecules throughout this process is exactly the same. The difference is their motion. While it's a liquid, they're going to be moving and sliding past each other, but once they change into a gas, they're going to be able to spread out and move. It's because we didn't have it in a closed container, spread out throughout the room. Now, when they leave the liquid, because they are at 100 degrees Celsius, the molecules as a gas will still be moving the same velocity as those molecules that were a liquid. Now, once they do change into a gas, their temperature is probably going to drop significantly pretty quickly because they're going to be colliding with other gas molecules that are at room temperature. But the initial leaving of that molecule from the liquid changing into a gas, they will be moving at the same velocity because the temperature is not changing. Now, in terms of the intermolecular forces, we spoke of that already. They are being broken here, so they're being weakened enough to where they're going to be completely broken. The energy change that's occurring here, because there is no because there is no temperature change, there's not going to be any Q equals mc delta T, so we're going to use that enthalpy of vaporization as a conversion to convert that mass into energy. And we see here that this is the only conversion that we were given in our data that has it measured in kilojoules. Everything else up to this point has been measured in joules. And the reason why is because to break all of those bonds, to break all of those intermolecular forces in water requires a significant amount of energy. So our 200 grams of water converted into kilojoules, and then we're going to make the conversion from kilojoules into joules so that we can have a reference, and we see this is going to be actually 454,000, and that is about 10 times greater than, almost 10 times greater than what the others were, because everything else was measured in, thousands or tens of thousands, and this is measured in hundreds of thousands of joules. So it does take a significant amount of energy to break up those molecules because, again, you are breaking all of the intermolecular forces. Once we have broken all those intermolecular forces, we can now see that we have a gas only, and because we have a gas only, we can change the temperature. One of the things I hope you can you've picked up on this here is that the only place that the temperature can change is when a material is in the one single state. So we can change the temperature when it's a solid only, we can change the temperature when it's a liquid only, we can change the temperature when it's a gas only. But when they are undergoing a phase change, like boiling or melting, the temperature is going to remain constant because the energy is going into changing the intermolecular forces, breaking them up a little bit, or in melting, or breaking them completely in boiling. not changing the velocity of the molecules. So our kinetic energy, because our temperature is increasing. Our molecules are moving faster, but they're in the gas phase. So really the only change in motion is that they are in a gas phase, and that they are going to be freely moving and not hindered by anything else. The intermolecular forces, we can essentially say that there are none for a gas. And that's going to become an important factor in our next unit with gases. In terms of the energy change, we can see here we're going to have our 200 grams multiplied by the specific heat of gaseous water, which I found to be 2.11. And then we have a final temperature that I had you guys max out at 325 minus the 100 degrees Celsius from where we were at boiling. And the amount of energy required to change the temperature of water from that 100 to 325 will be 94,950 or 9.5 times 10 to the fourth joules. Again, pretty large value, but here we're changing the temperature by 125 degrees, whereas before I think the maximum we changed it was 100 degrees, going from 0 to 100. So as you can see, we've got 5 very distinct areas on the graph. Each of them is going to require different amounts of energy to change those temperatures or change the state, with the melting of the water being the most energy intensive, where it's going to require the most amount of energy because you are boiling that water and breaking the attractions apart. Hopefully you have a better understanding of what's going on now. Make sure that you have corrected anything on your tables or your graphs. And if you have any questions, please contact me, and I will address those as well as I can.